Hello, everyone. Thanks for attending this session. My name is Sergey. I'm from Zinur, and also I have with me Ned from Tuxera. Ned is SMB expert here. And my goal for today is to provide you with performance comparing result of NFS and SMB protocols under ML workloads. So let's start from our motivation. We are developing high-performance block device which often used under parallel file systems like Lustre, IBM Storage Scale, and BGFS, but some of our partners demand for high-performance storage for small to mid-sized clusters, and there are three possible use cases. First one is small installation of several dozens of GPU adapters. The second one is large installations where our solution can act as a component under NFS flex file system. And the first one is a NAS on demand installation for GPU cloud providers. So I believe you have heard this many times. We need high performance storage to keep GPU busy because for now, the most expensive part of modern data center is GPU time. So let's start from NFS. Why NFS? So a lot of AI infrastructure engineers don't want to deal with parallel file system complexity, and they want to have some stable and simple solutions, and NFS fits good. So it supports, it's great for some of AI I/O patterns. It supports POSIX semantics. NFS has great performance features like NFS RDMA, TCP multistreaming, NFS local I/O, and NFS also has some great features for security and to operational efficiency. But we should always have some choice, and when we're talking about a NAS solution, the main competitor for NFS is SMB. For a long time, SMB was not have not been considered as a solution for Linux-only environment, especially for HPC-based environment, but SMB has very good performance features like SMB Multichannel and SMB Direct. And now when CFS client natively supports both, it's time to measure SMB and compare it head-to-head to NFS in pure Linux environment. So let's talk how to measure and compare. 3 years ago, ML Commons introduced MLPerf Storage benchmark, which allows us to simulate end-to-end training workflow and with different types of simulated NVIDIA accelerators with different types of workloads and models with different types of frameworks, not spending a lot of time and not spending a lot of money for infrastructure. So MLPerf Storage supports different types of models like image segmentation, image classification, and Cosmoflow. And now MLPerf Storage 2.0 has added support for checkpoint workload. And in the near future, we are expecting for vector database I/O workload. A couple of words about my test stand. So I had very simple test stand consisting of two nodes. First one, operated storage server running over RAID engine file system and NFS or SMB server above, and a single client having the same number of CPU cores. I've got 48 AMD CPU cores and the same amount of system memory, and server and client was connected with dual-ported 200 gig interfaces. So of course, I've got not the fastest nor the most modern hardware, but for majority of the market, 200 gig network is reality, 400 gig is too expensive, and so my main goal was to utilize the capabilities of 200 gig interfaces. So my evaluation was restricted to two workloads. First one is checkpointing, and the second one is UNet 3D training is the only workload supporting all-direct semantics and the most storage-intensive among MLPerf storage workloads. Last year at FMS, Micron provided information about MLPerf storage workloads. So here you can see that MLPerf storage 3D unit workload does only 120K block reads, and on the right part of the slide you can see the queue depth distribution with peak of about 45. So the typical MLPerf storage benchmark workflow looks like that. So first of all, we need to calculate minimal dataset size, having in the mind the amount of memory on the host, having in the mind expected number of GPUs. Then we need to generate dataset. Then we can run benchmark with different parameters, and after success, we can generate a report. And what is success mean? What does success mean? So, in terms of MLPerf storage benchmark, success means that we can provide simulated GPU with storage throughput measured in samples per second, while keeping average GPU utilization at more than 90%. So here you can see my command to run the benchmark. So as I said, I used NFS. I used MLPerf training for 3D unit and checkpoint. And for 3D unit, I enabled ODirect. And for checkpointing, I enabled F-sync operations. So NFS is a very simple protocol, but it's very easy to do badly. So I run my NFS server with default parameters and mount client with default parameters, simulated 8 GPUs, and you can see that I was stuck at 5% of average utilization, GPU utilization, but which is quite far away from expected 90%. Then I enabled RDMA, a very simple one parameter was changed. The performance increased almost 10 times, but I'm still unsatisfied with the results. That means I need to do some tuning. So the typical tuning workflow looks like that. First of all, we need to tune backend storage, especially we need to tune it for worst case scenario. Then we need to set file system correctly. After that, we can tune our NFS or SMB server options and enable some capabilities. After that, we can run first benchmark from client side to tune network, to tune NFS client options. At times, we need to change test parameters. NFS provides us with broad and very good set of tools to observe what is going on, to understand bottlenecks, to be sure that that parameters we implemented was applied on both sides, and negotiation between client and server performed well. And of course, I used all the tools during my tuning procedure, and also I had to utilize standard Linux tools like MPstat, PIDstat, PerfTop, IOStat to observe that system is not overloaded and everything is going well. So how to read the results? So for unit 3D workload, there are two figures. The first figure is the maximum GPU simulated when I've got success pass of the test. And the second figure is the average GPU utilization for such number of GPU. And for unit 3D workload, I measured additional CPU load generated by NFS or SMB server on my storage server side. For checkpointing workload, I measured checkpoint save and checkpoint load performance, and And again, I collected average CPU utilization time, CPU load, and also sometimes I ran simple FIO workload with sequential reads and writes for double check and to understand the maximum performance of protocol until some conditions, and all the results has been rounded for the ease of the understanding. So let's start from our server. So before I started with an MLPerf, I tuned my backend storage based off the rate because understanding the workload, understanding the queue depth and average block size, I was able to set up the rate correctly, and then I compared XFS and XFS with default mount and MakeFS options and with optimized options for my workloads. So here you can see that my file system was able, in the best case with XFS optimized, for my file system I was able to simulate 22 H100 GPUs at average utilization level of 94%. And checkpoints load and checkpoint save speed was about 28 gigabytes per second, which is half of the total performance of my backend storage. Okay, let's move further. For NFS server options, there are about 4 or 5 different options in NFS configuration file which impact the performance, and the most influential option is the number of NFS threads. By default, Linux has 8 NFS-D threads, which is not enough for high-performance NFS storage, and my recommendation is to set this amount equal to number of efficient CPU cores. Sometimes it could be less, especially when we have some high-performance backend storage, which requires some CPU resources. But according to my experience, it's not efficient to set this count more than real count of CPU cores. So you can observe the results. So increasing the count of NFS-D threads, we can see almost linear performance improvements for read operations, for training workload and for FIO sequential reads. But when I set the count of NFS-D threads to 96, which is twice of real CPU cores, I saw that the performance degraded. So I was able to run simulation of 9 or 10 NVIDIA H100 GPU accelerators, and the total CPU load increased up to 90%. And for checkpoint operations, I stack at 7.3 gigabytes per second for writes and about 17 gigabytes per second for reads, and this means I need further tuning for checkpointing operation. So here you can see some examples of MPT stats and PID stats for NFS threads equal to 1. System is very inefficient because we load only 1 CPU cores. But with NFS threads equal to 96, which is twice of CPU core count, we overload the system with NFS-D threads. So some outcomes, defaults are not enough, and one of my recommendations is to set the number of NFS threads equal to number of effective CPU cores. Sometimes you need to do less, take a look at your system load, but it's general recommendations, and there are different parameters of an NFS configuration file. I described them in the appendix to the slide deck. So when we are dealing with checkpointing, we have a lot of small sync operations. That's why I saw no performance improvement with NFSD count increasement. And there are two ways to improve checkpoint speed. First one is to disable W-delay option of NFSD server, because by default, Linux NFSD server has V-delay option on for write call async, but this increase the sync latency a lot. As a second option is to move from sync mode of NFS server to async. So here we can see comparison between NFSD server working with standard V-delay option enable and with no V-delay parameter enable, which allows me to improve the checkpoint performance almost 2 times. And as for async options, I see slightly better performance, but on practice, it tends to be unstable on more powerful system based on 400 gig interfaces. So I decided to stay on sync mode with no V-delay parameter set. And of course, we need to tune some NFS client parameters. And let's start from the NFS kernel module parameters. I have some recipes. I spent about 1 month finding the best numbers for each the parameters, and most influential parameter is max session slot, which means the maximum number of host static requests negotiated by client. And by default, most of Linux distribution has this parameter set to 64, which again is not enough for high performance read and write operations, and I recommend it to increase it at least 2 times. And this allows to improve training a checkpoint operation 15 to 30%. So for my installations, I saw about 15% improvement, but my kernel was I was using custom kernel with default parameters which is not equal to the default parameters of major Linux distribution, and comparing with default kernel provided by Ubuntu, the difference is about 30%. So, and the most influential parameters is client mount options. So there are 2 client mount options which impact performance a lot. The first one is in-connect, the number of parallel TCP or RDMA connection to one server IP for a given mount. And the second one is max connect, which allow us to get session trunking across multiple server IPs. And so working with high performance client, you can just set easily and connect to 16, which is the maximum possible parameters. And in case you have multiple IPs, you just need to spread this 16 connection across all the IPs. So I have several end-to-end examples for single IP TCP connection, dual IP TCP connection, and RDMA-based connection. So TCP and TCP multi-streaming allows me to increase read performance linearly, and as you can see, this parameter impact more on write performance than on read performance. Take a look at checkpoint write speed. So with TCP, multi-streaming, I was able to get almost the same performance for write operation as I got with RDMA connection. And having 2 ports and using NFS multi-tracking, I was able to twice the read performance. Okay, so it's time to talk about SMB. So now, can you take your part?
Thank you. Hey, folks. So I know you probably wouldn't be considering in an all Linux environment, just SMB wouldn't typically come up as a conversation, right? SMB has traditionally been a Windows protocol and a Mac OS protocol for the last 10 years. And NFS would be your place to go. But what you found out this week, thanks to Sergey and Zinor going through, is doing some actual comparison work with a modern SMB 3.1.1 implementation and sort of stacking it up with the exact same benchmarks and workloads, and found some pretty interesting results. If you're not familiar with SMB, like I said, it's the native protocol of Windows and Mac for remote file access. Supports Active Directory and Kerberos. You have multi-channel, which is very similar to what the multipath piece that was in NFS. It has RDMA support. And these things have been there for a long time. You probably have been to some SDCs when these things came out, around 12, 13 years ago. You might remember me from when I worked at Microsoft and worked on these things. Now, obviously, I work somewhere else. You get a lot of really sort of built-in niceties of high availability with SMB in a modern world, with transparent failover, sometimes called continuous availability, and scale out. So you have these things called persistent handles, where we retain information about handles from clients and can share them between servers in a cluster, so that the loss of a node doesn't result in loss of I/O or interruption in service for your app or your copy or your read or whatever. And that's useful things in a world of AI workflow where you're just pushing a lot of data, and hoping to, like Sergey pointed out, keep focused on the thinking of AI, keeping the GPUs busy, especially when there's service interruptions, because the less time you are spending burning up those GPUs, the less your AI stuff is making any money for anybody. Things get, if you were in the last VAST presentation, which was very interesting about talking about multi-protocol access, it was talking about the difficulties of transforming security between 3 different systems, but it's just as tiresome between 2. NFS and SMB have completely different security models. In our case, we will actually support doing POSIX as well as Windows ACLs, but our customers typically want to use Windows ACLs. They're typically using Active Directory. This is a ubiquitous system. And there are advantages to that ACL model that were around the granularity, inheritance, denies, things like that. Maybe those things are important to machine learning and AI, maybe not, right? I've seen plenty of discussions and demos of AI stuff at, say, Supercompute, and hopefully you'll join us there in a few months, where security and access control seem to be the last thing on anybody's mind. It was all just about how much can I push, what's the throughput, what's the fastest way I can go. But these are options for people who do care, and one hopes that people in the AI world would begin to care more about this. So a few things that we did. So what's important here to understand is this is not Windows client. All these numbers come from an Ubuntu to an Ubuntu. The Ubuntu server is running Fusion SMB, an SMB server, and then the client's just running the built-in CIFS kernel client. Steve French might be in here somewhere, his code, okay? We did make some modifications to up. These are things that are not necessarily default in Linux. We had to make quite a few tuning options. Upping the multi-channel count, upping the SMB max credits count, in order to try and push RDMA and the multi-channels past their defaults. Windows does a little bit more self-tuning here. Linux, you really have to get in there and make settings based on the workload. And I think everybody in here understands the difference between TCP and RDMA at this point. Maybe 10 years ago you might not have. But the idea here is to try and do as much RDMA as possible to offload the work on the client and the server. So instead of thinking about transmission, it's thinking about what the actual work is being done. That's especially important in these machine learning GPU environments where there's so much CPU being chewed up by everything. We want to be a minimum part of the problem. So I'm almost to the point of showing some numbers here. Hang with me. Just so you understand what we're dealing with from the Fusion side, this is a user mode. We also offer kernel mode server, but it's for Linux. It really is like sort of a direct competitor with Windows file server, for example. But we also support x64, ARM, PPC, and our goal is to push the throughput as much as possible. Like our goal is always around performance. That's how this product was built. Performance at scale. So if the theoretical limit of an RDMA 100 gigabit connection is 12.5 gigabytes a second, we try to get as close to that number as possible. Right now our number is around 11 and a half. It's pretty close, getting pretty close to the max. So if you buy 100 gigabit, 200 gigabit, 400 gigabit, 800 gigabit now from Mellanox, our goal is to basically make it so that your complaints are about Sergey and his storage need to keep up because the networks are getting so wide now that we're back to the storage being perhaps the bottleneck. So I did not want to put in too many specific numbers in here because we were still playing with this up until yesterday afternoon, but we will publish this set of things we found that worked perfectly well for Sergey on docs.tuxera.com, where we keep all of our perf tuning guidelines. But we have a ton of areas in Fusion where you're allowed to make similar changes like you can with NFSD or Ganesha or any other file server, right? Heavily around transport threads, VFS, op locks, and credits are areas here that all substantially influenced how the performance went when we actually compared the same workloads with NFS and SMB. And then, like I said before, on the client, on Windows, you actually have very few options to tune any of this stuff. But on Linux, there are more, and it turns out you should tune them. The defaults were not sufficient for us. We kept finding bottlenecks just out of the out-of-box configuration. So raising multi-channel and max channels, upping the max credits, finding a good mix of that for the workload and the type of, it was 128K, I think, I/O sizes was key during this exercise down in the I/O lab downstairs. And there are other settings here from the Linux side around the cache. I'll let you read these offline. This is not super exciting. So you're just using the regular mount command. This is not using the SMB client add-on or anything like this. This is native Linux kernel CIFS client. And we're just mounting it with, CIFS, aka, please stop saying CIFS, it's SMB, but it's CIFS in Linux. Mount point with forcing a version 3.1.1, making sure that we specify multi-channel being on, which is, again, not by default. And setting max channels, setting a higher credit number. And we did the same thing with RDMA because you can specify here, in the case of Windows, if you're doing all this, it would see RDMA and just be like, oh, you must want to use RDMA. Well, I'm not going to bother with TCP. Here you must be specific. And so these numbers look pretty good. And I struggle sometimes to understand how all this UNet 3D stuff works out because I'm not a MLPerf person by any stretch of the imagination. But you can see we are pushing with multi-channel on this first run around 20 to 22 gigabytes per second, which is a pretty substantial number. Remember, this is two 200s, so that number is pretty high. And then, working together, we made some further tuning pieces here, and I believe these were more around, And we got up to, eventually, on dual port, 48 gigabytes a second. And if you remember back to the NFS slides before, that is a pretty substantial number when compared. So if you look at these right here, you might guess over the years, and if I had had to put money down on it, I would have bet on NFS winning in these numbers. But that is not the case. The SMB performance was actually better under a number of circumstances. So, and because SMB has been now native inside of Linux for a long time, it's no longer this add-on experience or second-class experience. Arguably, you could say it'd be better to be using SMB on Linux than NFS for these workloads. Yes?
These are great. Was your writes for SMB, was it a synchronous style write?
You have to tell me this one, Sergey, I don't know. Tell.
Yeah, absolutely. Yeah. I did only
Use the mic. Use the mic.
Yeah, come up here to the mic.
So the question was about, did I use sync writes? I said, yeah, absolutely, yes. I used only sync writes with all direct options enabled, always for all the tests.
That is my last slide, all right?
Yeah, absolutely. So, as you can see, that SMB is quite good.
More questions?
Question?
I just have a quick question.
Yes.
Did you play with the SMB Direct credits, which are different from the SMB credits?
Those were the SMB Direct credits, I think, if I remember right. Is that right, Bastian? We were playing with SMB Direct credits?
SMB credits on the slide.
Were we using just SMB or not the direct ones? Okay, then they were just regular ones.
You should play with that.
Yeah, we should actually.
By default, it's fairly small.
Yeah, we were running around quite a bit for the last 24 hours.
Yeah.
There's probably more to be squeezed, yes.
Yeah.
Yeah. That's why I didn't want to necessarily publish my numbers yet until we were totally happy with them.
Cool.
Yes, sir.
Which kernel versions were tested?
So I used customized kernel 6.16 with NFS. So I had to enable some features. For example, by default, Ubuntu kernel have disabled SMB Direct, so I had to recompile kernel with SMB Direct.
I hate that about Ubuntu. Only on the client, not on the server.
Yeah, yeah. And for also I performed some NFS local I/O tests, and again I had to enable NFS local I/O.
It was otherwise
compile.
it was otherwise 2404, pretty vanilla. Yeah.
Did you try increasing the credit count on the RDMA transports for NFS as well?
No.
I noticed you were turning up the R size and W size on a couple slides. That's not supported in the client. Did you confirm?
So yeah, for client, for kernel version 6.17, it's supported. It was client side. At least, I'm not sure. I did not observe the real transfer size, but NFS stats demonstrated me that it was increased to for mega.
It sounds like pretty recently, like very recently.
Yeah, it wasn't supported in the server for 15.
Yeah, it was not supported in the server.
Other stuff for me, or is it back to Sergey? No?
Okay, thanks. So, as we can see, SMB demonstrated really surprising results, but NFS has some, NFS has some hidden A's. So NFS has NFS local I/O, allowing us to bypass RPCs and to get really good performance in case client and server side are placed on the same server. And inside the configuration, we can, when we need to build high performance solution, when we should write and read data directly and at fast performance from one server, and to provide some ability to read and write data from third-party server, we have an options to pass the block device directly to client side and to mount this device with standard file system, and then remount it with NFS. This gives us great performance improvement. And here you can see some additional comparison. So with NFS, NVMe or RDMA, I was able to get performance equal to local file system performance, if you remember from one of my first slides. And with NFS over TCP, I was able to achieve almost the same performance as a local file system performance. So for some configurations, we will need to provide high performance NFS shared to one server and not so performant NFS shared to another servers. We can build some disaggregated storage to pass some block storage directly to client side and to mount it with NFS Direct option, NFS local I/O options enabled. So I have in mind my next evaluation. So I'm going to prove the performance stability on a bigger and more realistic topology with more client and server nodes and maybe with fine-tuned 400 gig network. So I'm going to run my next evaluation, having 2 storage nodes for at least 4 clients, and to compare SMB and NFS again with more tuning options. With maybe I will tune some RDMA settings because up to now network tuning was out of scope of my work. I understand that RDMA tuning and network tuning can impact a lot, but I used my customized kernel, and it was not easy to build Mellanox Docker Fed drivers for my kernel, so I decided not to touch the existing network and to use with default parameters. So I think that's all. I have a lot of slides describing a lot of additional settings, but the most influential setting we described during our presentations. Any question? Yes?
Can we come back to the head-to-head comparison between NFS and SMB?
Yes, okay, sure. TCP or DMA?
Well, either. Yeah, I think so. Interesting observation. So even though SMB is better, CPU load goes up. In this particular benchmark, you're just doing AO, right?
Yeah.
In a more realistic scenario, with these nodes that are doing AO, would they also be doing compute?
Yes, but this is CPU utilization from storage side. I don't provide here the CPU utilization on the client side because the most of CPU was consumed by accelerator simulation.
Okay. So is it fair to say that even though SMB is faster, it is at the cost of additional?
No, it takes off the CPU. SMB takes out, I mean, that's the Tuxera implementation. Some would behave differently, but it's off the CPU of NFS.
And it's twice the throughput, twice the CPU, that's the errors.
Yeah, yes, but
Right, so 46% is what I understand.
Sorry, I was looking at the second row.
yes, I control, yeah. NFS, yeah, and the main reason that NFS was providing much lower performance, and NFS server had much lower load. Because with NFS, I was able, for example, comparing first 2 columns, I was able to run only 3 GPU simulated for NFS and 7 GPU simulated for SMB, and that's why I've got more than 2 times larger workload to SMB server, which of course increase the CPU utilization.
So whenever you have 3D workloads, as you have more simulated GPUs, the throughput over the network grows proportionally. go from 3 simulated GPUs to 6 simulated GPUs, you're pushing through about twice as much data.
Yeah, another option here is for reads, I think that's what you point out. It's actually consuming more space. For writes, it's the vice versa.
Yeah.
So I don't know why that would be the case, right? So it's anything specific to your assembly implementation that's optimized for writes but not for reads. That's what I see here. That's right.
No.
Yeah.
Large writes.
You would typically with us see any SMB implementation, right?
Sure. But this case, at least, I'm aware of what MLPerf does in this case, right? You meant 3D. So it's does one by reads and write, both cases, training as well as checkpoint, at least the IO pattern we have seen. So I'd assume it would be exact same IO sizes, both cases. So that's why I asked that question. So ideally, it should be comparable. Right?
Sorry?
Do the next slide.
Yeah, okay, yeah, sure.
The CPU should be, you hopefully aren't doing TCP in these areas. So,
So one interesting number would be CPU utilization per byte.
Yeah, yeah, I think, yeah,
cycle per byte would be an interesting.
yeah, absolutely agree. We need to.
Not cycle time, whatever
yeah.
measure, but
Yeah,
the scale.
Yes, that would be interesting to pull out here.
Here actually you can see that it has been reduced. It's compared similar to TCP. That's also something. I'm just looking at the last column. It was 46% as a case. It is 51. It's actually higher than that. Ideally, you would at least remove the networking part of it. Assuming it's IO.
You're also pushing what's
Okay, that's fair. That's fine.
You're basically
Okay,
getting what you paid for, you're getting
Sure.
the bandwidth. If you don't use the bandwidth, in my,
No, makes sense.
no, yeah, it's wasted money to.
So cycles per byte is flat between the SMB single port and dual port, but it's different with NFS, it rises, right? Goes from 33 to 65,
Yes.
right? 24 is about half of 51, so it's flat, which is good. That's what's expected with RDMA.
And I mean, when I remember the presentation for RDMA back in
2012, Greg, yeah.
They mostly said, okay, the reason for this is that we need to save cycles on the client, just for Azure, IOV at that point. Now for GPUs, having those statistics would be great in whatever the future version of your presentation.
That is the other part here, is the fact that on the client, in theory, the CPU usage of the main board, because we're not able to use the GPUs at all. Right? Theoretically, there's two sets of CPU numbers here, one of which don't matter to us, and we can't do that at all. It's probably not free. I'm sure that Intel or AMD would tell me how super not free it is to have lots of data flow around the motherboard between GPU drives and stuff. But there's the question now in the world of this AI workload about how much you care about the CPU to do the network transport. RDMA certainly, I would continue to keep pushing it, saying that it's ideal. But it's probably not as like crazy critical as before, because we're in contention for the same core as all of the workload and everything. And now the workload isn't actually using this. So let's say it's 50% higher on the CPU than it's otherwise not used. Maybe I don't care. In this case, it's not true because the MLPerf system is crap out of the CPUs. I would hope that maybe they'll be stuff.
It's the MLPerf benchmark is designed to simulate the actual stacks.
Yeah.
That's a big mess.
I've learned so much about MLPerf in the last 24 hours.
Client side, so this runs Python code to simulate GPUs. But server side shouldn't matter. But the other aspect, I think maybe I don't have to guys paid attention, right? It's interesting that the assembly form is much better, so I don't know how much of it is due to the protocol part. NFS is all transport, right? Versus in this case, multi-channel, you have different channel for the reads, right? For RDMA, right?
Yeah, I don't know how much is implementation of RDMA.
Yeah,
and how
yeah,
much
so
is
I'm
protocol.
just trying to understand how much of it is implementation versus the protocol itself, right?
It's clearly a combination of benefits, right? The protocols are different, but multi-channel smooths interrupts and events across the bus.
You can load up the
Lots of
machine with-
secondary effects occur.
You can load up the machine with a server on Windows, NFS 4 server, which all of this. And then you can also run a Slack. There's implementation specific difference where in theory the protocol, its limitations or advantages are the same. Yes, both Windows and Fusion follow the same protocol rules.
Argue that maybe in this workload, its protocol count is very minimal, given that these are larger items, right? So even with NFS, the overhead of that is very, very small, right? We're not selling very many small packets over the wire.
It is possible also for the packet size. It's very big difference over the NFS facility. It's possible here that NFS's RPC, the way they're handling packet sizes, reputation, other things here, could very well vary from what we're doing in SNIA. And I'd have to layer up the rest of it. It'd be interesting to actually look at wire capture.
Yeah, and this is all, it's RDMA as a transport, so
Yes.
you're saying
Well,
4K.
RPC.
RPC, right? Versus SMB has a separate channel for just reads and write over RDMA, and rest of the stuff is it.
SMB uses the same channel.
For small packets also? I thought
Well, they use the same RDMA connection, put that way.
Okay.
Is that what you mean by channel?
Yeah,
Yeah, because there's an SMB channel as well, but that's slightly
Correct.
different. That's a higher level
Okay.
structure.
so but do all the SMB requests/responses use RDMA channel or only reads and write?
When running over RDMA, they use the RDMA connection. They perform direct placement RDMA only for reads and writes. But it's a pure read-write workload. There's no
So
metadata.
will it map to an RDMA read write in libIPverse terms if you have to implement no user space or?
Yes, correct. RDMA
This
read
is
and write,
SDC.
direct placement, the tag, so-called tagged operation.
Okay, got it.
Yeah.
And you write up the whole metadata thing. That's probably where NFS was. Like PNFS and stuff, would take the crap out of us. If it mattered, it was purple. If it doesn't.
Okay, I think we're out of the time. 2 minutes. One more questions? Okay, thanks.